Hello. Hello and welcome to Deep Learning. Today we're going to talk about learning sequences and the transformer. I will start by introducing what does it mean to learn a sequence. So imagine you have a sequence of data, like for example, words in a sentence or stock prices. Predicting a sequence would mean, can we predict the next word, for example, in a sentence? Today I am very happy to be teaching this class. Can we predict the word class as next after seeing a piece of it, right? Or can we predict the next stock price, for example, for this deep learning course tomorrow after we've seen the stock price of this deep learning course in the last week or so? So we'll have some kind of a neural network called encoder, and we'll have a sequence. This sequence is going to be translated into numbers, right, or a string of digits. X1 is the value to the first word, X2 is the value of the next second word, and so forth. And by encoder, for example, we try to predict what is the next value out of a sequence. But what if we want to translate a sequence into another sequence? This is very typical. For example, in language translation, let's say I want to translate a sentence from English to Italian, for example. Okay, so I'll have an input sequence consisting of word after word after word, and I'll have exactly the same sequence learner that I had before, some kind of encoding. But this time I will also feed this output to a decoder. So this encoder is like, let's say it's learning the first language, and the second one is learning the second language, let's say. Okay. So what happens is I'm gonna feed the output of my encoder into the decoder. And the decoder is gonna be looking at actually two inputs. One is the output of the encoder, one symbol at a time, and then I'm going to start producing an output sequence, word by word in the second language. But at the same time, I will also feed to my decoder the previous word that I translated, let's say. Okay, so this is how this sequence learning is usually defined, and this model is called the sequence-to-sequence model. And we will see more details about it, but we need it today because we need to explain what the transformer is. And in order to understand what the transformer is, we need to understand attention. So attention is, for example, I want to give you like a fairly simple example that tells you what attention is. Let's say you have a sentence, for example, this one: the animal didn't cross the street because he was too tired. So when you read it, you don't know what it refers to. So you could be referring back to the street, or it could be referring back to the animal. We are not sure. So in order to understand what it is, we need to pay attention to the rest of the sentence, to other parts of the sentence. In general, attention is a process of cognition that is basically, designed to make sense of a large amount of data and try to figure out what is the most relevant information for a given task. And you use attention all the time. It's actually been studied in psychology for years and years and years, in neuroscience as well. But imagine, you're doing a task and somebody calls you, right? Your attention was on this task, but then when somebody calls you, you shift your attention to another person. Attention means that you have lots of things that you're around you, and you need to pay attention to the one that is most relevant. For example, in visual attention, let's say that I'm on a boat in a river and I need to be, looking where to go or where to stop my boat So what I'm gonna do is I'm gonna look at other things in the scene, for example, other people or areas where I could stop. And so instead of looking at the sky or the trees or all the body of water, I'm gonna look at specific areas of this image where that are important for my goal. This is visual attention, for example. Or when somebody calls you and you need to turn your face and look at their face, for example, or look at what they want. And this is the example that we've seen before of the sentence. So every time you listen to something, or you're reading, or you're paying attention to something, so this is a sequence of values. And again, in order to understand even a sentence as simple as this, the word "it" needs to be back correlated to all the previous word. So every time you listen to a sentence, you're keeping parts of it in your mind, and then as you get to a word "it" that could refer to multiple things, or even a word that could have multiple meanings, you need to go back into the sentence and try to figure out, okay, what did this mean in this specific case? And that is attention on word, or a word sequence, or a sentence. So neural attention, which is at the base of the transformer, is basically a neural network module that looks at a lot of data, and based on a query or context, for example, "it," we want to figure out where it comes from. So we're gonna go and look at the context of what "it" is, right? And then we encode the query in all the parts of the sentence, or all these pieces of the sequence, and we select the most useful parts. So let me get into the transformer. So transformer is one of the greatest innovation in the last 10 years of machine learning. And it's the transformer is a neural network architecture. And here I wanted to at least introduce what it is and how is it built. So the transformer, the original transformer paper, is basically a sequence to sequence a neural network. So it takes, for example, a sequence. So let's say it wants to translate a sentence from French to English, right? So inside of this transformer, we actually have the same encoder and decoder sequence of the sequence to sequence model that we've seen before very briefly. So it will take the input sentence, it will encode it, or the input sequence, it will encode it, and then it will pass it to a decoder, which will then decode it into the second language, or the second sequence. And this, by the way, the transformer is not just limited to words or sentences. It could be sequences of many other things, right? For example, we want to predict from a sequence of stock prices, we want to predict the sequence of stock prices of another company, right? Or something like that. Interesting enough, inside this encoders or decoders, there are actually many layers. They are identical, and that they are stacked together on top of each other. And the reason is because everything is composed of smaller parts, right? So for example, if I'm reading a paragraph is composed of sentences, and each sentence is composed by word, and each word is composed by parts of the word, the phonemes, right? So everything is sort of hierarchical, and this architecture is basically trying to do the same thing. So it has a hierarchy of levels, and you can think of it, at least for now, we can think of them as one encoding low-level features like phonemes, the second looking at words, the third looking at sentences, the fourth looking at a paragraph, the fifth looking out of a whole page, sixth looking of an entire document. Okay, so we can think of it that way for now. The good thing about it is that inside every single module, this encoder or decoder, which are actually all identical, so that makes it easier. There's another good thing for us that makes it even easier, at least for now, which is that if you look at this module, both the encoder and the decoder, they have feed-forward neural network, which are just a multi-layer perceptron, and we'll talk about it. And then the module that is interesting is this self-attention module that is repeated many times. So that makes it easy for us to really understand. So I guess for now we should take a look at what is this self-attention, right? So when we talk about self-attention, especially neural attention, is basically a neural network module that finds correlation within a set of inputs. So I call this input set IS. And so it turns out, for example, in the example of the sentence, the sentence is this input set, right? And we're gonna basically use word queries and keys, which are both copies, slightly different, maybe modified by a neural network, that can combine together, can generate an attention weight that can highlight important data. For example, if I wanted to find out what it refers to, I'm gonna have to look at it in the whole sequence context. So it could be like a key. Then I have to go back to the query, so the entire sentence, and I have to look and generate a map of what are the most important attention components. So for example, here, it might be very much related to the street or the animal, right? These are the things that are most typical. So I have to generate an attention mask that basically tells me, okay, out of this whole sequence, which part of the sequence are most relevant to the word it. And then with this attention mask, I can go back to values, which is again the same sequence, and try to mask parts of the sequence that I don't care about. So for example, going back to our sentence, when I look at it, I will get some attention weights, which are sort of represented by these colors. And then if I multiply the input sentence by these attention weights, basically I'm going to get out only the important portion. So like, for example, the street or the animal, and the rest is sort of masked. And this is how this neural self-attention is supposed to work. To give you like a very simple examples, let's say that I have a set of data called keys, and my input sequence is apple, oranges, and a banana, and then my query, for example, could be, okay, I want to focus on the apple. I'm gonna try to take this data and translate it into some keys, and then the highest attention value will be taken by one of these things and will be at the output of neural attention. I just want you to remember that all of this is actually not done with images or words, but it's actually a sequence of values. It's not really a sequence, it's an embedding. So it's a set of value, let's say 200 values or 200 numbers, or 20 numbers that represent a word, for example, in the sequence, right? So each one of these is a different word. And then at the output, I'm gonna get, a similar set of values that is basically the encoding of my input. And we'll take a look at that in a little while. So after we've seen sort of how this module work, remember that inside the transformer there's this self-attention module, and this is implemented in the transformer as a multi-headed attention, and this is probably the most difficult part, or the most important part that we should learn if we look at the transformer. So the multi-headed attention is basically this attention process right? But it's replicated in parallel many times, and whenever we replicate this self-attention multiple times, we call it multi-headed attention, which means that it'll take the same sequence, say 8 times, and it will look at 8 possible correlation, and it will output 8 possible correlations, right? So that's how it's implemented in the transformer, and the reason why you want to do this like multiple, it's like paying attention to multiple things in parallel, right? For example, if I go back to the sentence, I will have one attention output might be looking at the animals, right, when I refer to it, and the other attention output might be looking at the street, and the third attention output may be looking at another part of the sentence, and the fourth and other parts of the sentence, the fifth and other parts of the sentence that are maybe less relevant. Well, some of these outputs are relevant to the next layer and some are not. And so this is a diagram of multi-headed attention, and I want to explore with you a little bit, at least, what does it mean to do what is in this box here, right? Okay, so what we're going to do is we suppose that we encoded our inputs into a bunch of numbers. The multi-headed attention weight mask, it actually computes a dot product similarity. So whenever we look at this, there's a metric multiplication between the query and the key. This is actually the same sequence, the same input sequence is the query and the key, but they're translated by a neural network into some intermediate value. And then they're multiplied together, basically to try to compute a dot product similarity, right? They want to find correlation between the sequence of what does the word it could refer to, for example, and by doing this multiplication, we can find a correlation between, okay, it might be referring to a noun like, or a subject like animal or street, right? So this creates a sort of, it gives you the ability to find the similarity, and the similarity is then, it creates a weight mask, right? This weight mask is then multiplied again by the value, which is again the same sequence, and so that you can output the most relevant pieces of your sequence that you want to focus your attention on. And this can be a little bit abstract, so I found a way to represent it maybe visually. Is once you have the attention weights, so you'll have your input, which is an entire picture, for example, which contains lots of details, lots of characters or other things, objects in the scene. Well, the attention weights is basically creates a mask, right? That once you multiply it by the value, again, the value is an encoded version of the input sequence, right? So it's slightly modified input sequence, but you can sort of think of it as okay, it's the input sequence. So if I multiply the attention weight by the value, then the output of a multi-headed attention is simply actually the thing that I want to pay attention to, and it will mask everything else. So everything else is like reduced to low values, but the part that I'm interested in is stays at a high value. And a multi-headed attention will have multiple outputs, again, depending on the task, on the possibility of multiple tasks later in the is a sort of upstream. And then you'll have an output that will look at one object, one output that will look at another part of the object, and another part that will look at something else. And again, this image, you can think of it as a sequence. There's lots of details in there, lots of pixels, and it could be like a sequence if I'm reading them in a certain way, right? And so this gives you sort of an illustration of how multi-headed attention would work. And we'll continue in the next video.